Now I'm back to my original problem, where this time I don't want to assume that it is not deflected at all as a particle moves within the plates. So you can see the first thing I've done here is gotten myself a bigger picture. That's also, I mean, really important. You got to use lots of space, draw lots of pictures, and when things get complicated, there's no substitute for getting big piece of paper drawing big pictures, so you don't lose things trying to draw very small. So the particle comes in as it moves in the plates. It's accelerated up, and so it's going to experience a deflection. I'll try to draw that here, some amount. And then once it's here, it now has some final velocity. Well, final velocity from the plate's perspective, and it moves in a straight line until it hits the screen. Now, I want to define my terms properly here. L, of course, is the deflection from the center. That's how we defined it before. But it doesn't start in the second stage. It does not start at the origin in the y dimension. It starts some distance away because it was deflected some small amount in the plate region. So again, we're going to use our the same coordinate system that we had before, where this is y, positive y up, and then positive x along the beam line. Okay. So in this case, let's go ahead and look within the plates. We're going to look within the plates first. So within plates, stage 1, within the plates. Okay. So in the x direction, that's unchanged from last time. It's still uniform motion in the x direction, and so it travels a distance p, which is equal to its x component of the velocity, which is v naught times the time that it stays within the plates. So now let's look at, this is the y, the stage 1. Now in the y direction, so let's put our origin of y here on the beam line. So the initial y is 0. The final y is the amount that it was deflected, which I'll call here d. Amount deflected within the plate region. So the initial y velocity is equal to 0, and the final y velocity is what we called last time vy. And then again, we have still our same constant acceleration is equal to a. All right. So what does this give us? So it's a little more complicated than before. So now we still have that the velocity y is equal to a times the time within the plates. That's what we had before. And that leads to, get rid of this same expression we had before for the final velocity in the y direction, which is equal to the acceleration, the length of the plates, divided by the x component of the velocity. But now we have that the final y position, which is d, is equal to 1/2 the acceleration times the time within the plates squared. So if I just go ahead and substitute the time within the plates, that gives me that there is a deflection d, which is equal to 1/2 times the acceleration times the length squared over the initial velocity squared. So now I have, these a is my what I'm inputting, sort of what I want to be able to solve for some deflection L, and so now I have the velocity that it leaves the plates as well as the deflection within the plates in terms of that acceleration A. Okay, and that's what I got last time. I only needed Vy in terms of A, and this time now I've got Vy and D in terms of A. All right, so let's go on to stage 2. So in stage 2, again, the x direction does not change. It goes a distance q is equal to its x component of the velocity times time. Or that the time, this is now in the second stage, it's just called t, is equal to q over v naught. Now in the y dimension, we have to be careful, y direction. So we have our initial y is equal to d, right? Because it exited the first stage at d, so the initial y position in the second stage is d. So the final y position is L. And now the y velocity is v sub y. So we do just have uniform motion now. The acceleration is equal to 0. Okay, so in these expressions in the y dimension gives us that the final length is final y position is equal to the initial y position plus v sub y t, where t is now q over v. V sub y is a times p over v naught, and d is equal to 1/2 a p squared over v naught squared. And that's everything. That's all I need, all that information. So I can substitute all of those terms in now. The deflection is equal to the initial deflection within the plates, 1/2 a p squared over v naught squared, plus, substitute in for Vy, a times p over v naught, times then the t in the second stage, which is q over v naught. Now, at this stage, you always want to play with the algebra a little bit, simplify as much as you can to see whether you can come up with sort of meaning out of this. It looks like, what sort of common terms do I have here? Look here, there's a v naught squared in this term. This right here is a pq over v naught squared. So there's an a, p, and v naught squared in both terms. So a is equal to L is equal to L is equal to a p over v naught squared times q plus p over 2. And if I were, thinking about this, I would stop here and try to look at what this is. If I look at this term here, q plus p over 2, remember q is equal to 1.5, p over 2 is equal to 0.025. So the q is much greater than p over 2. Somewhere in there is, that's important. Somewhere in there is this correction due to the including the deflection within the plates. But let's go ahead and solve for a like we did last time. Solve for our x, the acceleration that we need in terms of L. Okay, so our acceleration then, if I solve for a now, is equal to L v naught squared over p q plus p over 2. Okay. And now, to be honest, a lot of students might just sort of leave it like this. But really, that's not what an experienced problem solver would do. There's meaning here that tells us something about what's going on in these relative scales, and we want to understand it more. And so now I'm going to introduce it, if you haven't seen this sort of thing before, to binomial expansion. And again, this may be new to a lot of people, but this is the sort of thing that really experienced problem solvers, they go to this right away. This is such an enormously powerful idea. The point is, I noticed something here. I have two parameters here where one is much larger than the other. And so what I want to do is I want to work this into something that looks like 1 plus x to the n, where x is very small. So how would I go about doing, and this not, if you haven't seen this sort of thing before, it's probably something you'd never think of doing. But that's why I'm doing it, because this is the way good problem solvers solve problems. This is how you would do this. So I can multiply the top and the bottom of q of this by q. Q over q is 1, right? So I can multiply the second term by q over q, and that factor, then I can factor I'll pull out a factor of q from that term. So what does this look like? L v naught squared over p q times, now this is 1 plus p over 2q. Now I still want it to look like this, and so I'm going to rewrite this again in even better notation. L times v naught squared over pq times 1 plus p over 2q to the minus 1 power. Now this is looking like something I can work with. First of all, look, what does this mean? First of all, p over 2q is equal to 0.05 over 3, right? Q is 1.5. So this is much less than 1. That's exactly what I wanted. I wanted something in this form, and now I have it. But look what this is telling us. If you set p over 2q is equal to 0, you get a is equal to L v naught squared over pq, which is exactly what we got in the last video. So our approximation where we assumed there was no deflection within the plates, the verbal description of that approximation, the mathematical representation of that approximation is setting p over 2q equal to 0. Well, let's see how good of an approximation that was. This, if I have here now, if I just go ahead and solve this, plug in all the numbers, I get an acceleration equal to 6.56 times 10 to the 12 meters per second squared. This is the full, the full expression. And you'll recall the approximate that I got from the last time was 6.67 times 10 to the 12 meters per second squared. And so that approximation is not good to two significant figures. It was good to one, but not two. It was got the answer wrong in the second significant figure. So I'm going to end this one invoking the power of the binomial expansion. So if you're not familiar with the binomial expansion, that 1 plus x to the n, if x is very small, is approximately 1 plus nx. I can turn essentially an arbitrary polynomial into a simple linear expression, as long as x is much less than 1. That is an unbelievably powerful mathematical expression for all of science and engineering. And we use that all the time, and so you want to be very familiar with this technique. So applying that, I can come up with another approximation for my full expression, but a better one using the binomial expansion. So it's sort of my A binomial expansion approximation now is equal to L V naught squared over PQ, where this, now invoking this relationship, just turns into 1 minus P over 2Q. And if I plug in values for this expression, I get, well, let's look at it in a more transparent way. I think this will be really good. So if we assume no deflection, this gives us an acceleration of this 2/3 10 to the 13 times 1, right? That's this 2/3 times 10 to the 13 is this. So we know that, let's get this out here. We know L over V naught squared over P times Q is equal to 2/3 times 10 to the 13. So if you assume no deflection within the plate region, that's setting P over 2Q equal to 0. And so you get just 2/3 times 10 to the 13. Our exact expression gives us 2/3 10 to the 13, that same term, times this term, which, if I calculate that out, is 0.9836. Where our binomial expansion then gives us 2/3 10 to the 13 times this expression, which is 0.9833. So you can see that the binomial expansion gives us to nearly 3 significant figures, the exact result. Okay, so, and maybe you don't need the exact result for this one, but as your computations become more complicated, these sorts of techniques become that much more powerful. So what have we learned from this problem? In some ways, it's just a two-dimensional, two-stage constant acceleration problem, but we've introduced some unbelievably fantastic strategies. The first of which is to take on a more simplified problem to solve first that gives you insight into the more complicated problem. Then, when you do, then you can tackle the more complicated problem with the knowledge you gained the first time. And then we talked a little bit about approximations and using the binomial approximation to give you more simplified results as well. Again, learning these sorts of things in the end won't take more of your time, but they allow you to solve more complicated problems and solve more complicated problems faster. It may seem like it took more time to solve the simple problem than just to go ahead and solve the more complicated one first. But if solving the more complicated one first simply means you sit there staring at a blank page for 2 to 3 hours, then it did not, in fact, save you time. That's the power of these sorts of strategies.